Yeah, so thank you for having me. It's nice to be here. Yeah, I guess originally the title of the talk was marginal operators in celestial Yang mills, but because I don't know how much of the audience is familiar with this field of celestial holography that has sort of blossomed in the last decade, I will sort of half of my talk will be uh, a review of the things that have been done. So to sort of set up the stage for what I wanted to talk about, which is the case of marginal operators in the boundary theory. And of course, stop me anytime if you have questions. Um, okay, so what is the big question that we're trying to answer here? This is not just our question we're trying to answer. This is a lot of people's questions is what is the theory of quantum gravity in 4 dimensions? There are multiple approaches to trying to understand this problem. So I'm not going to outline all of them, but one of the most prominent ones is probably string theory. And oftentimes we like to say that string theory takes what we call a top-down approach to this problem. So I don't claim to be a string theorist. I took a course in string theory once, but that's about all the string theory I did. But the basic idea of string theory is you say, well, I go into some higher set of dimensions and I have sort of a more wide variety of fields that I can consider. I have a very general theory, and then I try to constrain that general theory to give me something that is consistent with what quantum gravity should be. So I sort of have something very general, and then I try to constrain it, which is why we say it's top down. Okay, but in another approach, I don't want to say alternative approach, but another approach is this field of celestial holography, which has arisen in the last decade or so. We like to say that celestial holography is a bottom-up approach. So what that means is we take everything that we know about our current universe, so the standard model, and what interactions we know to exist, things that are experimental observables, and then we try to build up from that and say what can we add to it, how can we modify it in order to get a theory that is consistent with quantum gravity. So we start with something what we know, and then we try to add. Now, when I started working on this, I called these two things, alternative approaches or independent approaches to this problem. But actually, what I've learned is they're sort of complementary to each other. Okay, so string theory approaches it by starting with something larger and try to constrain. Celestial holography starts with sort of everything that we know and tries to add. And our hope is that one day the two will actually come together and we'll be able to connect the results that we have in celestial holography to the results that we know from string theory, since string theory has been studied much longer. Yes? What we know. Yes. So will that fit with celestial holography or that's I don't know whether I don't want to say that it's inconsistent, because at the end of the day, the goal was the same, to have a theory that explains all of the interactions in our universe. But the approach of celestial holography is different from that of grand unification. So what we know is field theory, right? Yes. And what is the problem with gravity in theory? It's just non-renormalized. Yeah, it's non-renormalizable, but we also don't know how something like a graviton interacts with a particle like a photon or a gluon or something like that. But we don't have a Lagrangian description that tells us what that interaction is. Good. It's just not renormalized. It's not when in your final picture. Yes. After adding, you are going to get back a field theory or something else. I mean, at the end of the day, you want to get a field theory description of everything. Okay, I don't know what that description is, but I mean, one wants to come up with a a method of adding in a gravitational field that is consistent and is okay. I don't know, the issue of renormalizability in this context hasn't been studied in great detail yet. Currently, the way to study it is sort of to talk about a graviton as a perturbation to your metric that you have in your space time. Um, so, okay, maybe we can talk more about the field theory description later. But okay, so this is sort of the base for how these two things should connect to each other. But where did this field of celestial holography sort of originate? So it originated in a study of asymptotic symmetries. Okay, so this is where you say, for example, in the case of, I can talk about gravity, I can talk about gauge theory. I say that I have some fall off conditions on my field. So let's say my metric, where if I go to very large R, where R is your spatial direction, I say that my field falls off like 1 over R or 1 over R square, and then I talk about what perturbations to this field are consistent with that fall off condition. So what preserves that fall off condition? And the necessity here is that your space-time that you're considering is what's called asymptotically flat. So all the fall off conditions ensure that as you take R to infinity, your metric is a flat Minkowski space metric. So if you do that, what you find is that there is a sort of space of possible perturbations that you can consider that will all preserve the fall-off conditions. And because those are all distinct, that's the notion of having some kind of symmetry where I identify it as a diffeomorphism that I can do to the metric, or a change that I can do to the gauge field or something like that. And these symmetries, because they preserve the asymptotic fall-off conditions of the fields, are called asymptotic symmetries. So in the case of gauge theory, these asymptotic symmetries are usually noted as large gauge transformations. And in the case of gravity, these are, so there are a few of them. The leading order one is called super translations. There's also another one called super rotations, and so on. So the nice part of these asymptotic symmetries was actually their connection to soft theorems in quantum field theory. So a soft theorem, as a reminder, is if I have some scattering amplitude and I append to it some external leg, like say a photon, then if I take the limit where that a photon's energy goes to zero, so then there is a factorization of the amplitude where I have some prefactor that's a function of the energy, and then I have the amplitude without that external leg entirely. And the insight that sort of started all of this was that if I look at these asymptotic symmetries, the Ward identities of the asymptotic symmetries are actually exactly the soft theorems. So when I talk about large gauge transformations, the Ward identities of large gauge transformations are actually equivalent to the leading soft photon theorem. When I talk about super translations, the Ward identity of super translations is the leading soft graviton theorem. So that is the first order in the expansion, soft expansion. Super rotations, likewise, are the next order in the expansion. So let me sort of draw for you a picture of what this means. So if I draw a Penrose diagram, this is, I'm talking about 4 dimensions. One can talk about higher dimensions if you want to, but 4D will be consistent. Usually what I say is I have some boundary here, which we denote as scri plus, and a boundary here that we denote as scri minus. This boundary is parameterized by a variable v, where v is t plus r. And this one is parameterized by u, where u is t minus r. And you understand r as the coordinate that goes from 0 to infinite. So as I take the asymptotic limit or the large R limit, I'm approaching the boundary of this diagram. These are past and future null infinity, which means that if I have some massless particle like a photon, it goes from past to future null infinity. And a massless particle will go from time-like to past time-like to future time-like infinity. Now, the reason you need two coordinates here, you need u and v, is because when I look at the large R limit, right, going to this boundary, I actually need two coordinates to parameterize the entire range of t, so from minus infinite to infinite. You can convince yourself of that fact by just looking at what happens to these coordinates when I take R going to infinity. And so what we usually say is we say, well, I have, whatever process I'm talking about, whatever field theory I have, is occurring inside this diagram. And then I'm looking at sort of what I can observe at the boundary, which is usually some kind of radiation, which is why it's related to these soft theorems that I talked about. But the insight of the celestial holography program was actually that if I draw this diagram and I take, for example, a light cone, then I can look at a point here. And because this is a four-dimensional space-time and I'm drawing it in 2 dimensions, this point here actually corresponds to a 2-dimensional sphere. Okay, so every point on this boundary is a 2-dimensional sphere. And what we call this is we call these spheres celestial spheres. And because I have asymptotic symmetries, all of these, technically there's a sphere at every point, but super translations in particular tell me that I can identify all of these spheres with each other. And actually, I only need to talk about one sphere. I don't need to talk about it at each u. I can always translate in u, and that's a symmetry of my space-time. So the celestial sphere here is a 2-dimensional sphere, as I said. And by a nice parameterization of momentum, what I can do is any amplitude, like scattering amplitude that I talk about here, that has, say, some incoming particles and some outgoing particles, each of these can be identified as some point on the sphere, okay? So if this is here, I have some insertions that correspond to my incoming and outgoing operators, or incoming and outgoing fields. And there is, in fact, an identification that tells you that each of these fields corresponds to an operator insertion on this 2-dimensional sphere, okay? And the final piece of the puzzle that you need is that if I write down my momentum, so this is for momentum as conveniently omega, where omega is an energy, 1 plus zz bar. So I've chosen a convenient parameterization that allows for, this is a massless momentum, but p squared is 0. I can write down a massive momentum as well. It's just, it looks different. But for this particular discussion, I won't concern myself with massive particles. I'll only concern myself with massless particles. If I do this, then these coordinates z and z bar actually correspond to the angular coordinates on this 2-sphere. And if I perform a Lorentz transformation in 4 dimensions on this p mu, what it looks like in zz bar is actually a Mobius transformation. So that's the one where z goes to az plus b over cz plus d, where the determinant of a, b, c, d is 1. The Mobius transformation, so the usual conformal transformation that you have. Yeah. The Lorentz transformations in the bulk. So if I take a Lorentz transformation of this you can just do it. I have to parameterize the Lorentz transformation matrix in terms of these A's and B's nicely so that it shows. But if you do that, you can show that it just looks like a Mobius transformation of Z and Z bar. No, so technically the sphere is divided into two. You're right. You have one part of it which is associated to past null infinity and one part of it which is associated to future null infinity. So so technically there is a z at past null infinity and a z at future null infinity. But there is a relationship between those two, which is an antipodal matching relationship between them. So yes, but you're right. There are two different ones. So what this means is that if I have a theory in the bulk that has Lorentz symmetry, then I can, by using this parameterization of the momentum, this Lorentz symmetry is actually manifest as a conformal symmetry on this two-dimensional sphere. So sorry? This description, the sphere metric is a specific function of C. Correct, is a specific function of C. So the sphere has to be parameterized by two angles, usually theta and phi. So you write this down as like it's like tangent phi e to the minus I theta and tangent phi e to the plus I theta. So they're complex conjugates of each other. But in a lot of literature, you will see actually that you can, they are complex conjugates in the case where the bulk spacetime you're talking about is 3,1 signature. But one can do a Wick rotation to 2,2 signature in the bulk, which means that the Z and Z bar you write down are actually real and independent. But usually we talk about it as complex conjugates of each other to sort of make contact with the usual 2D CFT. Which parameter? So this is the momentum of a massless particle, right? All I have imposed here is the fact that this has to have p square equals 0. Only on the boundary this parameter is valid? No, this is everywhere. So what I do is, to actually show this explicitly, I take some scattering amplitude that I have. I can take, for example, whatever I want. I can take massless scalars. I can take, gravitons, photons, gluons. It's all been done in the literature. I take some four-dimensional scattering amplitude. I write down the momenta in this way for the massless particles. Okay, and then what I have to do then is I have to take, so if I call my amplitude in 4 dimensions as A, right, this will be some function of omega Z and Z bar. Then what I can do is I have to, assuming this is only a function of massless particles, I take a product. So I take, if this is some n, I integrate over all the energies. And this gives me some new thing, where essentially what I've done is I've changed out the energy label for a delta label. Okay, this is a Mellin transform. And what this does is, it's actually not as complicated as it looks. Usually we write down scattering amplitudes in a momentum space basis, right? All your wave functions are eigenstates of momentum. But what we do here is we switch out the energy for this delta, which is identified with a conformal dimension. And so these guys are actually now written in a new basis where your wave functions are eigenstates of the boost operator. Okay, so the eigenvalues of that this delta. So now this ends up being a function of delta I, Zi, and Zi bar. Okay, and you can write it out and you can do this transformation and show that if I, for example, take a 3-point function, say in the bulk, and I perform this Mellin transform, then this operator that I have on the boundary actually looks like a conformal field theory 3-point function. It has the right power law structure, it has the right dependence on the deltas. So you can directly verify that if I took some Lorentz invariant scattering amplitude, I do in fact get something that is a conformal field theory correlator. Okay. So in this way, and as I said, there's also a different transformation in the case of massive particles. You just have to add in a bulk to boundary propagator and integrate over. Yes. No. Okay, I'm going to get to that actually in 2 minutes. So I will address that question. Other questions? So delta is identified with I'm going to answer that in 2 minutes. That is the question of exactly what delta is, which is something that has been studied in great detail.
The following, right? If you change B, then C changes, right?
Yes.
I
correct. That's why this is some function of all the zi bars.
Guys are coefficients on the say for the power.
Yeah.
Which is charted with a particular coefficient.
Yes.
And for the past, you have another chart.
Yeah, but there is a matching relation between the coordinates, so you're able to write it out in terms of yes.
And that chart, that coordinate system, in terms of that coordinate system, the sphere has a particular.
Yes.
Usually, if we have a 10-point amplitude, we integrate over omega, diverge omega goes to zero.
So in all the cases that have been done thus far, you don't actually need to worry about the divergence as omega goes to zero.
Yeah. Let's say add some virtual correction.
Yeah. Yeah.
Amplitude is still dependent, Q dependent.
Yeah. Correct. So generally speaking, yeah, you can think of the delta as a regulator because technically the omega goes to zero. So what I mentioned before, the soft theorems, right, is essentially what you're saying where omega goes to zero. And if I have to actually find out what happens when omega goes to zero, then I have to be careful in it actually corresponds to a limit of what delta has to be. So if you want to actually look at specifically the regime where omega is zero, then you have to talk about how to properly take that integer value limit of delta. But when you actually do the Mellin transform of this guy, because you have this power on omega, you end up getting something that is well. I should say it's finite, save a delta function in the sum of the dimensions of the operators, but. The infinite integral?
Does it make sense to say that the amplitude makes an arbitrary large energy? Because if it is, let's say, F1 amplitude something, how do we know that F4, F5, or whatever don't matter?
Sorry, what is F4 and F5?
Higher order connections. In a way, it's
so okay, so I should say so far most of what has been done, I would say probably 98% of what has been done at tree level. Okay, so all you have to do is look at the range of validity of the tree level amplitude that you want to consider. Now, I'm not remembering off the top of my head, but I know there is a paper where they explicitly look at which are the amplitudes where this Mellin transform is well defined. And it's you can do it in the case of, I think, they did it for one type of string theory, I forgot which one it was, as well as for Yang-Mills, and also in the case of gravity.
Right hand side has the values. Inside we just have A, and that is like the low energy effective theory, right?
So
With the tree level, the amplitudes, the maximum energy is controlled by the scattering. If you want to go to infinity, so energy cannot go to infinity, not the scattering.
Yes.
You need infinite energy.
Right, but it seems to be that even the single of you
That is from 0 to infinity. That's correct. No, that's correct. We don't usually write this as a cutoff. There is no cutoff here.
It's not. If you have complex scattering, where do you take omega? There's an upper limit. Total S or
so, an external leveling, right? It's an external momentum.
Yeah, omega is some external momenta that appears in your scattering amplitude.
It's not arbitrary.
There is.
Some momenta is zero, so it gives you constraint.
I mean, this thing includes the momentum conserving delta function in it, right? So it has that, which is actually what in some gives rise to this delta function in dimension. So I should also say that it's not something that I necessarily understand very well because I haven't gone through the math myself, but there is a paper where they do study exactly what happens when you look at amplitudes that have some strange behavior in the UV. I don't know the results well enough for myself.
AN will have the constraint.
Which constraint? AN has the delta function, yes. Yes.
It's not that if one is the one is there will be a cutoff because there is that delta function. I'm asking you a question that the right hand side seems to have information.
Correct.
Can you identify?
So UV and IR do correspond to some particular limits of what delta is. But again, that's not a result but I can definitely point you to the paper where it's, and I'm happy to talk to you about it, but I just don't know off the top of it. Yes. Yeah, essentially everything that's done is tree level. Everything that I will talk about today is also at tree level. Yeah. Okay, so if we decide to accept that we can indeed take some amplitude and transform it, then we do get something on the right hand side which transforms like a conformal correlator. And so the notion from here is that okay, if I take all of these scattering amplitudes and I transform them, I have some set of conformal correlators, or correlation functions that look like conformal correlators. So there's probably some conformal field theory that lives in this two-dimensional space here. In fact, if I consider a theory of gravity, then if I look at the second set of asymptotic symmetries, which are the super rotations, okay, these, as I said before, correspond to the next, not leading, but subleading soft expansion. Then there are, in all cases, there are operators on this two-dimensional sphere that correspond to these symmetries. So basically, the insertion of them generates the soft theorem mode identity. And in the case of super rotations, the operator that you need to insert to get the associated Watt identity is actually a stress tensor in the 2D CFT. And so you can take that stress tensor, you have your usual Virasoro generators, and you can write down your standard Virasoro algebra in that case as well. So if I have a theory of gravity, then this also tells me that gives me more evidence for the fact that I do indeed have a two-dimensional CFT on the boundary. Okay, so but what was the goal of all of this, right? So the goal was, the goal of having such a duality is if I start with some theory in 4 dimensions, say my fictitious or non-existent theory of quantum gravity as it is, then I have a duality to a 2-dimensional theory, conformal field theory that lives on a boundary. And 2-dimensional conformal field theory is nice because it's very well studied. There are many possible CFTs that have been written down, and we also, it has a infinite set of symmetries that can constrain the correlation functions, etc., etc. And we can use all of that to hopefully constrain what the bulk theory of quantum gravity should be. But that's sort of the ultimate goal. In order to do that, one needs to actually define what this CFT is, because we don't know what it is. All we know is that there probably is one because we have a stress tensor and we have this relationship that tells you that I have conformal symmetry and that I can transform things to correlation functions. But I don't know what, yes?
Spatial gauge solutions like instant. They have a scale.
No, nobody has considered instantons in this case. But the question is, what CFT is it? Okay, because otherwise we have no way of telling anything about the bulk theory.
Is there any space of CFT that you could consider?
Good. Yeah, so I'm going to talk about the constraints that we know so far. Okay, and that's what I'm going to tell next. So most of the work so far has been to try to understand aspects of what type of conformal field theory it is. Okay, if I write here, it can be seen. Okay, so these CFTs that live on the boundary have been called celestial CFTs. And so in order to answer this question, you say, okay, well, usually if I have a 2-dimensional CFT, I say that the CFT is defined by my spectrum of operators, so they're conformal dimensions, and the operator product expansion coefficients. Because once I know that, I can define all of my correlation functions. And if I know that in the case of CCFT, then I have all the correlators on the boundary, and I should be able to just go backward and completely define whatever the S matrix is of quantum gravity. So now to address the point about what is delta here, okay, so that's the first thing is, what is the correct spectrum to talk about here? Yeah, so there are, as I said, this transformation exists for massive particles as well. So I can talk about massive amplitudes. The transformation is mathematically more difficult, which is why a lot of work hasn't been done in that context. But the operators in celestial CFT can correspond to massless or massive fields in your bulk theory. So basically this gets modified by a bulk integral of a bulk to boundary propagator. So essentially it's, you have to think about it as there is some hyperbolic slice here that is in 3 dimensions, and your massive field ends up here, but you smear it along this whole thing with a bulk to boundary propagator and identify it with a operator that lives on the boundary. Does that answer your question? Maybe. So okay, we can talk about that too. But as I said, most of what has been done has been looking at only the massless sector of whatever theory you have in the bulk. There are some results for massive, but it's very, very little. Yeah. Yes. Yeah.
And it's a consequence of whatever symmetries you had in the bulk.
Correct.
Like
correct. Well, so the infinite dimensional symmetry that you're talking about actually comes from the fact that, for instance, in the case of super translations, okay, I didn't write it down explicitly here because that wasn't the point I was trying to make. But if I talk about super translations, they're actually parameterized by a function on the sphere. So there are infinitely many of them. I can make many such transformations. Each one of them corresponds to a different diffeomorphism of the metric. But maybe that wasn't what you're asking, is it?
No, I'm saying
Okay.
so whatever you said applies to flat space. Let's say.
Yeah, absolutely. Actually, most of what is done is in flat space.
Standard model with gravity.
Okay.
In the bulk and set up a perturbation theory.
Okay.
That theory is non-renormalizable. Okay, but you can counterterm renormalize and define the theory within a particular length scale or energy scale. Within that energy scale, that answer is reliable, and you calculate scattering amplitudes. Those amplitudes will be consistent with these symmetries.
Yeah.
And therefore, they will be consistent with this conformal invariance on the sphere.
Yeah.
The problem with non-renormalizability is that you have to keep tuning it, and there are infinite number of parameters. And therefore, you will end up getting a complicated CFT there. How do you expect to solve that problem here? It's not clear to me. The more you correct the bulk theory, because your construction is reliant not only on dynamics, it is only reliant on the symmetries.
Yes.
If you modify your theory, if you fine-tune the theory, or not fine-tune, just modify by running the scale, everything is consistent with symmetries. Yes. And therefore will be consistent with conformation.
Of course. So you're I think
so you keep correcting on the CFT side.
Sure.
Therefore it doesn't solve the non-renormalizability.
Okay. So I think your question is sort of related to the sort of larger question of exactly what is the entire set of these CFTs that you can talk about, because you're correct in saying if you make some modification to the bulk, whatever it is, whether it is adding in some field or whatever modification, it will modify whatever the CFT is on the
energy scale in the bulk will become a parameter in that CFT and it will modify.
Yeah, so
and the parameter will change the theory in the CFT.
Yes, I don't disagree with that.
You are rewriting the same thing
in
a different language.
Correct.
I didn't see any ingredient which will solve non-renormalizability problem. If that is a problem, I don't think that's a problem.
Okay.
If some people believe that's a problem, I didn't see any ingredient that would solve that problem.
I don't know of so everything that is done here is, as you said, is a rewriting of what we already know about the bulk S matrix. It is not, I mean, the fact that there is a correspondence between these two symmetries is just a fact about these symmetries and their group structure. But if I find some other theory that is consistent with the symmetries, it'll give me something different on the boundary. So no, I don't think there is my point of this talk is that there are sort of many questions about exactly how one defines that theory on the boundary, which is why the end goal of actually trying to understand the bulk theory is sort of kind of far away. It's not, one needs to really understand what it is here and how it's consistent.
This is also a holographic theory.
Yes.
And if one believes that gravity is, this seems to be different. And while you may see somewhat of a connection between the non-renormalizable gravity T plus 1, that may not be exactly as you may think.
And I didn't quite
I didn't follow that comment. Maybe we can go ahead.
Yeah, we can talk after, maybe this is a better discussion from that. Okay, so how exactly do we understand what the spectrum of operators is here? Initially, I think somebody brought it up before. When people were writing down what these transformations were and exactly what the basis of wave functions was, these deltas had to lie on what's called the principal unitary series. So that meant that they were complex. They were actually 1 plus I lambda, where lambda is a real number. And if you did it that way, then you could show that this transformation was nicely invertible. It formed a complete basis. The states were delta function normalizable, and so it seemed like that was the correct basis to be talking about. So most of the initial literature was writing it in that case. However, this whole thing was based on the soft theorems, and I mentioned to you that the soft theorems are actually generated by some kind of insertion of an operator on the boundary that one refers to as a soft operator. The soft operators are actually those that have dimension delta as an integer. So constrained integers on any integer, but it's delta as an integer. And so naturally, the only one that will appear on the principal unitary series is delta equals 1. You'll never have any others. And because these are the operators that we want to talk about, it seems like, well, maybe we should be actually trying to understand a basis of just these soft operators. And in fact, in the last couple of years, there have been a few papers where people have talked about a basis for this CFT that consists of the operators that have integer dimension. Okay, so currently this is sort of the basis of operators that we work with. The fact that they have integer dimension can be seen by the fact that if you take a amplitude and you take a soft expansion, right, each term in that soft expansion is going to be some power of omega, 1 over omega, 1 over omega squared, etc., or 1 over omega order 1 omega, etc. And when I do this Mellin transform, I can, and to actually find what the soft theorem is on the boundary, it basically looks like taking the residue of each of those poles. So each of those operators corresponds to taking the residue with respect to the energy. And this is the way that you treat the omega going to 0 limit properly in this. Okay, so that's sort of one aspect of the spectrum. But I said the other thing that one wanted to know is what are the operator product expansion coefficients? And there's two ways in which you can go about this. One is by just constraining via symmetries. At this point, there are many papers where they've done this. And basically what you say is based on whatever bulk theory I'm talking about, I'd say that if I want to consider the operator product expansion of, I don't know, 2 gravitons, then it should contain operators of a certain conformal dimension and certain spin. And then I can impose the Poincare symmetry from the bulk, and I can also, impose the asymptotic symmetries that I have to basically get recursion relations for what these OPE coefficients are. Yes.
The bulk you have string theory, over the coupling constants and interactions can come from the single theory which has single parameter. Right? Now, what happens is when you have a standard model, gravity, all have coupling parameters.
Yes. So the coupling constants usually appear in this as a coefficient of this amplitude. It's just the coefficient that appears in the endpoint functions. So the endpoint functions are constrained to have a power law dependence, but generally there is some C that appears in the top, right? So the coupling constants that you have in the bulk will just appear as those coefficients. Yes, here we don't have a Lagrangian. Yeah. So here, since we don't have a Lagrangian description for this CFT, maybe one day we can, but we don't actually understand what that parameter would correspond to in this. It's only, most of the time it's set to 1. So there's also that, but it appears only in the coefficients of these guys. So, and also in the, as some scaling of the operator product expansion coefficients.
I guess if you had known the Lagrangian in the CFT, then they will carry all those.
If we knew the Lagrangian in the CFT, that would be great. But I mean, we have no way of actually defining what.
In principle, they are there in the theory.
In principle, they should be there in some capacity. Everyone has to actually determine what the terms are in the Lagrangian to actually find that out. Okay, so one can find the OPE coefficients by symmetry constraints. The other way to do it is by looking at splitting functions in the bulk theory. So if I look at this here, I realize that each of these corresponded to some particle that is coming out here, right? So if I say this is some P1 and P2, then if I take P1 and P2 to be collinear, then that takes these momenta to be in line with each other, which brings the operator close to the other operator. So I can understand a collinear limit of my bulk scattering amplitude as giving me what the OPE is on the boundary. And so for most of these scattering amplitudes, you have a nice relation where if I take two momenta to be collinear, then I have a splitting function that comes out front multiplied by an amplitude that has n minus 1 particles. So if I take that and then, Mellon transform in this way, I can also obtain the OPA coefficients, and it turns out these two things are consistent. So there are sort of two ways in which you can do this. Okay, but what I wanted to say, there's a lot more to say on this, but maybe I'm sort of running low on time. What I wanted to say is we have at this point we have understood a lot about how we can start from a bulk theory and obtain some conformal field theory on the boundary. Okay, but as has been reiterated many times, we don't know what conformal field theory that is. And ideally, what we would like to do is independently study what this conformal field theory is, because only then we'll be able to get something like, say, a Lagrangian description or some description of the theory that is sort of independent of what we already know in the bulk, and then be able to go backwards. So I don't think so. It doesn't need a Lagrangian. It would be nice if it had one, but yeah. Again, I mean, as I said before, what defines the CFT is the spectrum and the OPE. So one doesn't necessarily need one. So there are people who say there are few aspects. Yeah, there has been studies about it saying it's a log CFT. There is also the no, and I think so. I myself am not very familiar with the papers with, I think there was actually a very recent paper on log CFT stuff, but I think that actually comes from one needs to look at more terms in the soft expansion from the bulk point of view in order to actually obtain that it is a log CFT. There are currently no strong statements about exactly what kind of CFT it is. In fact, there is, yeah, I think right. So to the end of trying to understand what kind of theory this is, one way, so there are multiple ways in which people have gone about this, myself included. One can try to consider, sort of in vain with what you were telling earlier, what happens if I add some fields into my bulk theory. I say, okay, I was only considering Yang-Mills before, I was only considering gravity before. What if I couple it to a scalar, or what if I couple it to some other field that appears in the bulk? And in that case, I will get modifications to the operator product expansion because I will have new terms that appear effectively coming from new 3-point interactions in the bulk. I will have some new set of soft operators because I will have soft operators corresponding to whatever fields I inserted, probably. So I can do that, and that's also been studied. I can also, as I said, most of this has been done at tree level. One can try to expand and go higher than tree level and say what happens at loop level. That's a much harder problem because, for one, you need to actually know what the amplitude is at loop level, and most of those expressions are, one, more complicated, and two, also suffer from, when you actually try to transform them, oftentimes suffer from divergences, which are still not very well understood. So there's been sort of minimal work trying to understand what happens at loop level, but okay, one can try to see how that affects the boundary theory as well. The approach that that I have sort of taken recently is, so I guess what the point of the talk was, but okay, I can sort of say it briefly because the details are not particularly important. But it's to actually understand if there is a space of CCFTs using marginal operators. So what is a marginal operator? In general, I can have my spectrum of operators can include marginal operators without messing with the conformal invariance of the theory, right? Marginal operators are those that have, so in my case, I'm talking about dimension 2 CFTs, so delta equals 2, but in particular, H and H bar are 1 comma 1, where these are the usual left and right conformal weights. So if I translate that, that also means that it's a scalar operator, right? So this is a scalar of conformal dimension 2. And if I add that in, then I don't change my conformal invariance. But from the bulk perspective, what I've done is I have somehow modified whatever the bulk theory is because I've added in some operator. So one way to try to study this is to understand what are the possible marginal operators that I can add into my theory, and maybe that will give you some information about ways in which the bulk theory can be modified. Yes. Anything I would say.
Your operator, they satisfy the Jacobi.
Good. So. Okay, so when you calculate the OPE, this will give you some, OI, OJ goes to something. In the usual way, I can mode expand those operators and I can find some commutation relations between their modes. One expects that the commutation relation of these modes satisfies the Jacobi identity. So what you can do is you can say, people tried to do this, but it didn't actually go as far as we would have liked. What sort of operators can I add in to what deformations of the OP will they correspond to? Is it consistent with the Jacobi identity? If it's not, then maybe we can throw it out as something that is allowed to be in the bulk. There were some results on this, but it was not as I don't know what to say, not as concrete or strong as one would have liked. So I think it was sort of, there was also the issue of a part of the community wasn't sure whether Jacobi identity had to be satisfied in this case or not. I think majority of the people say that it should. So far, everything that we have is consistent. So no, of the CFT. So the CFT, again, there are people who will tell you it should be unitary. There are people who will tell you it should be non-unitary. But actually, currently, so I think last year there was a paper where they actually found a more concrete dual between some bulk theory and a CFT. It was some sector of a bulk theory and a CFT, but in that case, the CFT they considered was non-unitary. So it was some, I think, had the Liouville field or something. Mm-hmm.
Some aspect in the bulk.
What does the non-unitarity translate to? I don't know if I have an answer to that question. Sorry. I think it's a valid question to ask. I don't have an answer for it.
I like
Mm-hmm.
What are the restrictions that I need to satisfy?
Yeah, I think not. Other than the symmetries that have to be imposed, there are no other restrictions that are known to further constrain. Yeah, we don't know the full spectrum itself.
I would even know the operator exists.
I mean, we have some operators that we know to exist based on the soft theorems.
The operator should also exist. Jacobi identity is one that I know. Yeah. What else are being demanded here?
on some closed algebras.
Why should it be closed? I mean, it can be infinite algebra, it is an infinite algebra, so it can go on.
Questions. So there have been, I'm not an expert on that, but there have been studies of looking at quantum field theory from the S-matrix point of view, without having a Lagrangian. Trying to find the conditions or consistency conditions for this. If that is known for, so to say, quantum gravity, then shouldn't one start with those restrictions on the bulk side and derive the restrictions on the CFT? Like what are the properties of scattering amplitudes in a quantum gravity field? Start from that and translate. All that is being done here is you are translating Lorentz language to conformal language.
Correct.
So
Correct.
if you study that conditions for the scattering amplitudes in a quantum gravity theory, and then those are naturally written in terms of the Lorentz language.
Yeah.
Translate that into a conformal language.
Yeah. So I think again, I don't think that approach has been taken, and so some people have. I think some people have studied what are the implications of like crossing symmetry, but other than that, I don't know what has been studied on the boundary side from that. So
I think it's studied for any specific or subclass of physical theory in the bulk.
Yeah.
Has the details of the CFT.
Yeah. So in particular, some of the most studied parts of the bulk are the MHV sector. So both of gravity and non-abelian gauge theory, they have studied the MHV sector. And in fact, it looks very much like, so there are several papers showing that one can write down some CFT on there's some celestial CFT that, as I said, involves a Liouville field as well as I think some fermion fields that it's coupled to that generate all of the MHV amplitudes in the bulk. But maximal helicity violating. So this is a certain sector of, for example, all graviton amplitudes or all gluon amplitudes where the helicities are given to you. It's 2 negative helicity and all positive helicity. Tree level. Yes, tree level MHV amplitudes. Yeah, right. So maybe in the last 5-10 minutes or so. So as I said, I wanted to say what happens if Okay, yeah. Well, I think there was a good discussion about all of this anyway, so that was what I came here to do. So, can I add in some marginal operators into this theory to try to understand possible ways in which I can modify the bulk theory? The first question one has to answer in that case is exactly how does one construct a marginal operator? How do you understand a marginal operator? So we did look at this problem in the case where whatever you had in the bulk was a nonlinear sigma model. So effectively, the operators you were considering were scalars. And in that case, it was relatively easy to construct marginal operators because if you're only talking about scalars, the operators on your boundary are going to be scalars. So all I have to do is pick one that has dimension delta equals 2, and I will have something that can be identified as a marginal operator. And in that case, actually, the marginal operators were identified as what are referred to as shadow transforms, which is a particular type of integral transform on the 2-sphere. So integral in Z and Z bar. So these were shadow transforms of soft scalars. So that is the operators that correspond to the insertion of a soft scalar field. And so there were some nice properties where we said, okay, I can look at, I can try to understand commutation relations of soft limits, and we had some nice results about that. But what we want to talk about is actually a bulk theory of gravity, right? Scalars are nice, but ideally, we want to be talking about what are the marginal operators on the boundary when we have some bulk theory of gravity. And in that case, one actually has to understand how do you compute a marginal operator in the case of gravity. Unfortunately, I don't know the answer to that question. What I do know is how to construct a marginal operator in the case where instead of gravitons, I have gluons. Yeah, so essentially what it does is, so since the bulk theory was a nonlinear sigma model, there was a target manifold associated with that nonlinear sigma model. And so there was a space of vacua that you had in that theory. And when I shifted essentially by adding in a marginal operator on the boundary, what I was doing was shifting from one vacuum to another vacuum in my bulk theory. So I was doing a vacuum transition. So additions of marginal operators corresponded to vacuum transitions in the bulk. So that's why there was sort of a nice. Correct. So the web of the scalar, so I should say here that the addition of the marginal operator essentially amounts to a change in the action of the form lambda I d square, let's say z mi of z, where this is the marginal operator and this is some parameter that sort of specifies how much I have deformed by, and the web of the scalar changes essentially by this lambda.
So exactly marginal operator, then you'll probably get differentials.
Yeah, so there is so there is a notion in this case of an actual manifold, right? So that's sort of what I was trying to get to, is I say, well, I have, okay, I can only draw in 2 dimensions, unfortunately, but I say, okay, this is some manifold of all the possible conformal field theories. Each point here corresponds to some conformal field theory that is valid, but in going from one to another, I have to add in some set of marginal operators. So these marginal operators essentially give me directions that I can move along this manifold to get equally valid conformal field theories that have a different operator spectrum. Okay. So in that case, you're sort of moving along some line, which was why we had some notion of saying, well, if I have some, I can think of doing like some kind of a box where I come from one side to another. In the usual case of some manifold, you would say, okay, this is the curve, measures the curvature, right? If I come back to the space and it's the same, then that means there's no curvature, otherwise there is curvature. In the bulk theory, what this corresponded to was essentially what happened in the case of scalars, what happened when I took the commutator of 2 soft limits. So I said I want to have amplitude where I want to take 2 particles soft. What happens if I take particle A soft before particle B versus particle B soft before particle A? If the manifold had curvature here, then that commutator was non-zero. So that was sort of the nice result in the case of the sigma model. So it's I don't want to say holographic. I will say dual.
So it's structure. It's a property of 4 dimensions.
4 dimension. It's a property of the fact that you have Lorentz symmetry in 4 dimensions. Not necessarily. As I said, you can do this with massive particles as well. But I don't know if you can construct a marginal operator from a massive. I don't know actually how this story works out in the case of massive particles. I would imagine not. It's already difficult in the case of massless. Yes, I mean the soft theorems that I mentioned, there are a universal property of the scattering amplitudes, right? Yeah, so in the case of the scalars, it was nice because you sort of had this nice picture, but okay, so gravity is a little more difficult. But yes.
You can capture here.
Yes.
Is it possible for me to demand that 3-level amplitude? if I sort of increase the momentum of external particle to infinity,
Hmm.
still I get a finite. What will be that condition in your CFD? Can you impose that?
Sorry, can you say the condition again?
One of the nice features is that if you have a very highly excited participate, if they interact at level, the amplitude won't diverge. Right? That means another thing you will problem.
Yeah.
So in which way, what have you ever thought of imposing that on CCFT?
But this is specifically in the case of a massive excitation, right? I don't know if that has been thought about actually. I don't know what that constraint would imply on the boundary.
Once you classify everything like that.
Yeah. So if you want a quantum gravity,
like whether the theory is renormalizable or not, whether the theory is renormalizable or not, it is possible to read it out from
renormalizable comes when you go to hard group level, right? When
but even at the tree level, even at Fermi interaction, for example, even at the tree level, energy growth will tell you that it's not going to be renormalized.
Kind of coming to that. See, if you want a quantum gravity, it's necessary that if you go very high energy, also your amplitude actually has finite value. So if you know how to impose that on CCFT, then that can actually lead you to a quantum gravity, right? Or
Yeah,
something.
yeah. So I will unfortunately say again, there has been one paper where they studied the implication of UV behavior in the bulk UV behavior on the boundary amplitudes, but there hasn't been any paper since then on it. So I don't know, and that's not a paper where I can recall the results very easily, but so I don't quite know what that would imply for constraints on the boundary, unfortunately. Okay, so as I said, one would want this for gravity, but gravity is difficult, primarily because I said this shadow transform is some integral transform on the sphere. If I try to do the same thing, so first of all, if I want to consider a marginal operator, it has to be a scalar. Obviously, in the case of gravity, I'm not talking about scalars, I'm talking about spin 2. So I need to somehow take them and try to transform them in such a way that maybe I can transform them to some scalar operator. But in the case of gravity, there are no transformations like this that will allow you to do that. In fact, one can write down all of the allowed transformations on the sphere, integral transformations on the sphere. They form a group. It's this dihedral group of order 8. It's the symmetries of a square. So there are 8 of them, including the identity. There is a shadow. There are 2 light transformations, as they're called. There are 2 transformations that are related to the shadow transform. And there are 2 other transformations which I have dubbed as half shadow transforms. None of those will allow you to take a graviton or a spin 2 operator and transform it to something that is marginal. However, I can transform to something that is marginal if the operator I'm considering has spin 1. So in the case of a gluon. So what I considered was sort of a toy model where instead of talking about gravitons, you talk about gluons. And in that case, you can construct marginal operators. There are 4 such operators you can construct. I won't write them down. It's not particularly enlightening to see what they are. But so what that allows you to see is that there are 4 possible directions in this manifold that I can, in this manifold picture here, that I can sort of deform the conformal field theory to get an equally valid conformal field theory. And so that is on its own interesting, but as many people have said, it would be nice to understand what that means from the bulk point of view. And as of now, I don't have an interpretation for what exactly these operators are from the bulk. I don't know I don't know if there is some, in the case of the sigma model, there was this nice story in terms of vacuum transitions. I don't know if such a story is the case here because I don't know what set of vacua that would correspond to. So at the moment, all I know is that I can construct some set of marginal operators that give me a some full set of valid CCFTs that should correspond to some sort of deformation of the bulk, um, whether it is a shift in the vacuum expectation value of something, or maybe it is the addition of some valid operator or interaction in the bulk. But so right now, sort of the open question in my mind is what exactly it corresponds to, which would sort of I think would give some information about the bulk that we don't have as yet. But of course, this is in the case of Yang-Mills, not in the case of gravity. The hope is that there is some analogous construction when I talk about gravity and spin 2 particles. Maybe I take some composite operator that can be understood as a marginal operator, or I have to take a descendant of instead of a primary operator, take a descendant to get it to have the correct properties. But I'm still working on what happens in the case of gravity. But the point I wanted to make here, just to sort of close it all together, is most of the work that has been done has been going from what we know here to try to understand what a celestial CFT is. In my mind, I think that's a little saturated at this point. I think we sort of done all we can by taking everything in the bulk and saying, okay, what can we determine about the CFT? We sort of need to work on how to go backwards. So my method of trying to do that is to try to understand from the CFT point of view what marginal operators I can add to, understand the space of these theories a little better, but that also seems to be a little difficult. So I'll sort of leave it on that note. This is what we understood so far.
Is there any limit of momentum, or is there a region in the momentum space, the space of momentum of external particle, where I can make this an a holomorphic function? This depends on Z, not on both.
Oh, so I think usually in the case of these the tree level MHV amplitudes, these are actually entirely holomorphic amplitudes, if I'm remembering correctly. But as I said, this thing has a momentum conserving delta function, right? So I don't know. Okay. Generally, I can write down this in terms of spinor helicity variables, right? I can write it in terms of like, these guys, Ij and Ij, where these are related to like, I take some, I can, these are related to the usual Mandelstam variables in some certain nice way. And so these guys are related to Zij, which is Zi minus Zj. And this is a momentum space. I'm not transforming anything as yet. These are related to Z bar Ij. And if I look at this, technically this amplitude should have some nice structure in terms of these variables. And since this transformation here in the case of massless particles doesn't depend on the Z's at all, if this amplitude is only in terms of these, or I can write it only in terms of these using momentum conservation, then this will be something that is entirely holomorphic, and vice versa.
So then, like if I have such a limit, then by looking at the behavior of the function, that holomorphic function, on the dependence of that holomorphic function on delta, can I study the high energy property, the UV property of that amplitude? So like, because if you don't have enough damping factor coming from AN for this energy.
Right, so you're talking about the omegas that appear here, right? Yes.
Yeah.
Yes.
So that integral will diverge if you don't have.
Definitely, and that's exactly what was done in the paper where they talked about what the conformally soft theorems are. So the analog of the soft theorems on celestial sphere, they did look at exactly how many factors of omega you need here in order to make this a valid transformation. So as you exactly said, that you need a certain number, a certain power of omega in order to have this be something that is not divergent. And that's where they said at tree level you can consider this set of amplitudes in order to have something that converges nicely.
So if I like demand now if I look at AN and then
This
can I use that as a restriction on your CCFT to get or construct amplitudes which has nice UV properties? So by just doing this complex analysis, is it possible to put a constraint on your CFT?
Wait, I don't understand why it was necessary for this to be a holomorphic or anti-holomorphic for your point, or was it not?
No, just to like use the power of complex analysis.
Okay, so what exactly are you saying you should be able to do with?
Because see, in the left side, I know that there is a energy integral.
Right.
And I will go to UV also, right? So that part, and the theory knows how that UV behavior is, right? Now, if I reverse it, that I want a quantum gravity or a theory which can
okay. So
good amplitudes.
Deduce somehow, I see. But one then in that case, one would need to know. Oh, okay. So let me rephrase to make sure I understand. So are you saying if I start with some correlation functions on this side that
and within a kinematic domain,
with some domain, okay, and then I say what, use this to say what powers of omega I require in this initial amplitude in order to have something that was well defined to give me that.
Yeah,
so work backwards to get this. I don't know if
the
that
delta is knows, like I think that delta
this will have the information about delta.
Yeah, you
Correct.
have to choose delta to make sure that even if the amplitude is diverging at high energy, still you want to make AN finite, right?
Yes.
So that delta knows about this UV behavior, right?
Yeah.
No, even at tree level, when you say an amplitude is finite at tree level, right?
But Rosie, if you control the omega dependence of AN on the left hand side, it will eliminate graviton. Because we know graviton interaction is not renormalizable and it has an energy growth. But at tree level, if you control the energy growth too much, you will eliminate graviton altogether.
No, actually, even if, let's say it takes when you say an amplitude where like one of the externals, like let's say the corresponding closed string amplitude, you can study the graviton interaction, right? Even there, the graviton interaction will give you finite answer, right? Why not?
Only all of string.
No, that's what I'm saying. If you are looking for a quantum gravity,
that is different from the tree level in field theory.
No, that's true. That's why I'm saying you are going from CFT to bulk. So what kind of condition you should put on CFT?
This is the tree level field theory diagram.
Yeah, see, actually, her like long-term goal is trying to get quantum gravity, right? From celestial CFT.
Correct.
That can you put constraint?
As a general thing, that is possible.
Yeah, I don't. So I don't think that has been looked at as yet. I guess my only concern would be that if you try to
just to give a counterpoint, if you use the higher derivative of gravity, then it is controlled. And we have demonstrated one particular higher derivative is even renormalized.
Okay.
So that is why it is controlled.
Yeah, it's controlled. No. What I mean is, of course, you modified gravity.
Yeah, of course.
And then it is controlled. And then one can ask, what does that translate, as he puts it, into the current CCFTs?
One could ask that question. True.
As a
Modified gravity.
Sure.
No, the mathematical exercise that we are doing here, that's equally well.
That is right.
Okay, other question.
Yeah.
About this particular.
Oh, yeah.
This Malin moment amplitude. What is the role of this? Does it mean that the amplitude? I mean, QFT, I know that actually photons are gluons. If you look at the amplitudes, these energies are coupled actually for W1 plus W2 plus W3. There's a constraint, and then you cannot separate out independent gluon emission or photon emission unless you do this Malin moment, right? Because they're coupled, they're convoluted in some sense. And because the amplitude is convoluted with respect to all the energies, the Malin moment actually separates out. Actually.
Yeah.
Is that what you are doing, or what is the
What is the goal?
Goal of the integral actually.
So,
For me actually, it does not obvious that you do an integral and then you get something.
okay. So
is it separating out
it's separating out each one independently, right? Because now you have an independent dependence on delta 1, delta 2, delta 3. Yeah.
Just can I make one? This picture that you just showed, you did not have you did not have action for the conformal field, right? You are just writing it.
So no. So if I had an action, right, this would be what I did.
The relation between lambdas and the space-time field. Exactly what happened is the relation between worldsheet and space-time in string theory also.
Okay.
This relation is exactly the same.
Okay.
So one might focus on
One might try to.
Why that is the case.
Okay.
Probably the structure dictates is one. This only thing that is possible, but one should make sure.
Okay.
This is exactly the same. In the worldsheet, if you take that kind of a deformation, it corresponds to a deformation in the space-time.
I see. Thank you. Yeah, as I said, I took string theory a long time ago. So I will look at that actually. That's a good point. Thank you.